Okay, let's go ahead and get started. This is video lab for lab 8 for General Physics 2. And I'm going to set up some resistance configurations for you to look at. And when we do resistance, I don't have an ohm meter directly that will measure equivalent resistance. So what we're going to have to do is measure current that is produced by the different resistor combinations. Okay, so the first thing I wanted to do was to show you my battery. Okay, so we've got my battery configuration here. I'm going to work really hard because these circuits are fragile. And so I've got 3 batteries in series. Each one of these is a 1.5 volt battery for a total of 4.5 volts. They break apart easily. I told you they were fragile. And so then we have a voltmeter here. I don't know if you can see that dial. There's a lot of glare there, but it actually says about, oh, that's not really saying anything. To check my leads. Bend this a little bit. And it's reading at about 4.3 volts. It's difficult to see there. I'm going to try to get it without the glare, but you're going to have to take my word for it. 4.3 volts. Okay, so we have 4.3 volts worth of energy source. Some crazy glare, isn't it? And then we're going to test different resistors. The first resistor is this one here. I'm going to hold it up directly to the screen without the glare there. So this is a 680 ohm resistor. So the resistance given by this is determined by the blue band, which stands for 6, the gray band, which stands for 8, and then the brown band has a multiplier of 10. So you take 68 times 10, and that's 680. Then I have 2 other resistors, okay, that are equivalent. They're the same, and they have 2 orange bands followed by a brown band, and each one of these are 330 ohm resistors. So I'm going to show you some different configurations of these resistors, and then we're going to check, first of all, we'll check the resistance of each one of these resistors and make sure that it is lined up with what is printed on the resistor itself, and then we will try the different resistors in different combinations. What you're going to do is calculate the equivalent resistance, and then we're going to measure the equivalent resistance. Okay, so here we go. Okay, so I take away my voltmeter here. I just have a plain old open circuit. The red is hot, and the black is ground. Okay, so I'm just going to put those down. You can't really see them right there, but I'm going to see if I can get the dock camera to share in just a second, and we'll get these going. Okay, so what I'm going to do next is I'm going to take my Ampmeter, that's got an A on it for Ampmeter, and I'm going to check the resistance of each one of my individual resistors. Remember the battery configuration is 4.3 volts. So I should be able to use Ohm's law to tell me what my resistance is as long as I have my voltage and my current. Okay. So I take my first resistor, which is presumably 330, and then I put it directly through the current meter. I'm going to use the smallest scale, which is 50 milliamps. Sure everything's connected. Okay, and I'm barely getting a reading. So this troubles me. Make sure that this is complete circuit, which it is a complete circuit. So if I have 4.3 volts and my resistance is 330 ohms, then how many milliamps should that give me? Okay, so let's go ahead and calculate that out. I'm going to use my calculator. Okay, so I have 4.3 volts. So that says 4.3. Then I divide it by my number of ohms, 330 ohms. Then multiply by 100,000, and that gives me 13 milliamps. Okay, and I'm seeing that right now. I want to double check and make sure that I've got this right, because I'm getting 13 milliamps as my calculation, but I'm getting something much, much less than that on my amp meter. So I'm going to pause the video and see if I can get this to work. Okay, so it turns out I just had a loose connection, but when I put this 330 ohm resistor in series, then what I get is a current of 13 milliamps, which is what I would expect. That's what I calculated. And so that confirms that this resistor is 330 ohms. Okay, so take that one out. Take my other resistor, which is also 330 ohms, and check it. It gives me the same value. So this is indeed 330 ohms. Then I can take my final resistor, which is 680 ohms. And that gives me about 6 milliamps. And with 6 milliamps of current, that does confirm that that's about 680 ohms. Okay, so next what I'm going to do is I'm going to set up 4 different circuits. And what I want you to do is, using the principles from chapter 23, I want you to calculate the equivalent resistance. Okay, so I'm going to go ahead and pause the video here, and then I will show you the circuits directly. So the first configuration that I'm going to show you is 3 resistors in series. Okay, so I'm going to try to do this. My document camera is not working, which makes me not very happy, but I'm going to try to show you this so you can see correctly 3 resistors in series. Okay, so you've got 3 resistors in series. The first one is 680, the second one is 330, and the third one is 330. So now take the time to calculate equivalent resistance for that. Okay, so you're going to calculate equivalent resistance, and then we'll check our answer together. Okay. Okay, for 3 resistors in series, all you have to do is just add the resistance of each resistor. So we have 2 that are 330 ohms and 1 that is 680 ohms. So our equivalent resistance, just get out my calculator here. So we take 330 plus 330 plus 680 equals, and so our equivalent resistance is 1,340 ohms. Okay, so check that with your answer, make sure that's what you've got. When you have resistors in series, all you're doing is you're adding the resistance around the circuit. Okay, the resistance is additive using Kirchhoff's loop law. Okay, so the next thing that we're going to look at is if we take our 3 resistors and we put them in parallel. So now we're going to have a parallel circuit So draw out a parallel circuit on your lab sheet, and we'll have 3 resistors all in parallel, 330 ohms for 2 of them, and 680 ohms for 1 of them. So that will give you 3 resistors in parallel. And I think I'll do this next portion at the board, so I can hopefully show you the equation that we use in order to calculate resistance in parallel. Okay, so for 3 resistors in parallel, then we take the reciprocal of each resistance and we add those together, and then we take the reciprocal of that. So the reciprocal of 1 through 3, or the resistance of 1 through 3, is just equal to 1 over R1 plus 1 over R2 plus 1 over R3, all to the negative 1 power. Okay, that's Kirchhoff's node law. Okay, so when we use Kirchhoff's node law, and I apologize, I'm going to try to get some of this glare down, but it's almost impossible with this room. So essentially, all we have to do is plug in numbers. So resistance 1 through 3 is equal to 1 over 330 ohms plus 1 over 330 ohms plus 1 over 680 ohms. All of that to the negative 1 power. Okay. We take that all to the negative 1 power, and then that gives us, let's plug it into our calculators. So you take the reciprocal of 330 plus the reciprocal of 330 plus the reciprocal of 680. Okay. Then you take the reciprocal of that, and I get 133 ohms. So our resistance, equivalent resistance there, is 133 ohms. So go ahead and check your answer on that calculation too. Now let's do a slightly different configuration. Okay, so for this next configuration, what we'll do is I'll draw the configuration up on the board. And then we'll calculate the equivalent resistance. So let's say I have my power source here. Okay, so that's my power source. And then I have one branch of my circuit. I have one resistor that's 680 ohms. And in the other branch of my circuit, I have another 2 resistors each that are 330 ohms. Okay. So in that instance, in this first branch, we have a 680 ohm resistor. And in the second branch, we have 2 resistors, one 330 up here and one 330 down there. Okay, so try that one on your own. Figure out what the equivalent resistance is, and then we'll come back and we'll calculate that for you. Okay, so back to this problem. So the first thing that we want to do is we want to simplify this diagram. So since these 2 resistors right here are just resistors in series, we can add them together. So 330 ohms plus 330 ohms gives you 680 ohms. So we can erase that and simplify it to one resistor. And that will give us 660 ohms. Then we have 2 resistors in parallel. This first one is 680. The second one is 660. So we go ahead and we put those together and using Kirchhoff's node law. Okay, and then I'll go down a little bit here so you can see the bottom. And then we know the resistance between those 2, our equivalent resistance, is just 1 over 680 ohms plus 1 over 660 ohms to -1 power. Okay. We go ahead and calculate that. So we take 1 over 680. One divided by 680 plus 1 divided by 660. And we take reciprocal of that, and we get 335 ohms. Okay, so there are other ways that we can do this. There are 6 different combinations of how you can do this, and we've already done 3 of the combinations. So for the last combination, what I'm going to do, we've done all of them in series, we've done all of them in parallel, and then we did 2 in parallel with 1. And so what I'm going to do is, I'm going to use the same basic configuration. Now, we're going to change this one to a 330 ohm resistor. This will be 680. This will be a 680 ohm resistor here, and this will be a 330 ohm resistor here. Okay, so that's our 4th configuration. So now at this point, what I want you to do is go ahead. Can't see that whole thing, I do apologize. So I want you to go ahead and calculate out what the equivalent resistance is for this. Okay, we have 330 in parallel with 680 and 330 in series. Okay, so go ahead and calculate that out, and then we'll compare answers. Okay, so when we do this particular problem, then we have 2 resistors in series. Those are easy enough to take care of. We have 680 plus 330. So that's going to give us an equivalent resistance in this branch of 1210 ohms. Okay, we just add those together. Okay, so that's our resistance there. So now we have 330 here, 1210 there, and these 2 branches are in parallel, so we can use Kirchhoff's node equation just to tell us that our equivalent resistance is equal to 1 over 330 ohms plus 1 over 1210 ohms. And that will give us, oh, we take that to the -1 power, whoopsie. And that gives us an equivalent resistance of 259 ohms. Okay, so what I want you to do with this particular section of the report is go ahead, write out all of those current loops, okay, write them out, and then show me your calculations for equivalent resistance for each one. So you're going to have 4 different sets of calculations on that, and with those 4 different sets of calculations, then you're also going to have equivalent resistance. Okay, next thing I'm going to look at is part 2 on capacitance. So I'm going to pause the video, and then we'll set up our capacitors. Okay, so I've got my entire setup here. I've got my batteries right now. My batteries are charging my capacitors. Okay, so here are the capacitors, so the battery is charging them. And then I've got my resistor here. That's my 680 ohm resistor right there. And then I've got my voltmeter here. Okay, and the voltmeter is reading approximately 4 volts. It's maybe a little higher than 4 volts, but we're going to say that 4 volts is times 0. And then I'm going to time this with my phone, and I'm going to give you the time points in seconds for where we reach 3.5 volts, 3 volts, 2.5 volts, 2 volts, 1.5 volts, 1 volt, and then 0.5 volts. And we're going to watch this discharge after I disconnect the batteries. So I'm going to shout out the numbers. I can't really show you directly on my phone, but then you'll be able to just do a linear plot of voltage versus time as the voltage decays. And then you'll do a log plot where you'll take the log of voltage versus time. Okay, want to check? Yeah, the logarithm of voltage. You can do just a base 10 log, or I'm sorry, a natural log of voltage versus time, and that should give you a linear graph. Okay, so you're going to do those two graphs as part 3 on your tutorial. You aren't going to do the RC circuits tutorial. That's computationally based, and it's just really, really untenable to do this online. So, but we will do this experiment right now. Let me get my phone. And as soon as I get my stopwatch out, then we can start time. And we can see when this reaches the different voltage benchmarks. Okay, so I'm going to go ahead and start time and simultaneously disconnect the battery. And we'll say that our 0.0 is 4 volts. Start, disconnect, and start. Okay. So we are already at 3.5, so that's 3 seconds. At 6 seconds, we're at 3. At 10.5 seconds, we're at 2.5. At 16 seconds, we're at 2. It's getting a little harder to see. At 25 seconds, we're at 1.5. And at 37 seconds, we're at 1. Going slower and slower to slower decay. And at 1 minute, we are at 0.5 volts. Okay, I'm going to repeat that. I'm going to pause the video and we'll do that one more time. You can pick either one as your run, but right now I'm going to recharge my capacitor. So that will take a little second. So I'm going to pause the video and we'll run this one more time. Okay, we're going to try this again one more time. Okay, I got my batteries off the camera here. Here they are. I'm going to disconnect my battery and then at the same time press time. And then we'll go ahead and plot out, I'll shout out the time, and then you can plot out the time in linear and log graphs where you have voltage versus time, and then log voltage versus time in 2 graphs, and that will satisfy part 3 on your lab handout. Okay, so here's my 0 time, hit start, then I disconnect, and right away at 3 seconds we're at 4 volts, 7 seconds we're at 3.5, at 10 seconds we're at 3 volts, at 15 seconds we're at 2.5 volts, at 21 seconds we're at 2 volts, and at 30 seconds we're at 1.5 volt. It's starting to slow down. And at 42 seconds we're at 1 volt. Going slower and slower and slower. This inching in there. And at 105 seconds, 1 minute and 5 seconds, we're at 0.5 volts. Okay, so go ahead and plot that out. So I'm going to have you plot that out. And then once that's done, you can go ahead and turn in the lab report. So you're going to do part 1, where all you're doing is you're showing your 4 circuits and you're calculating the equivalent resistance of the 4 circuits. And then you're going to do part 3, where I want you to have a data table with your time and your voltage, and then also 2 graphs, one linear and one log graph of voltage versus time. That's what you need to turn in. It's due next Tuesday. That will be April 7th. And I want you to turn it in by email by 5 o'clock. Thank you.